Now we discuss the quantum theory of hydrogen atom. So in this first class, I will discuss the separation of variables. That means how to separate the three-dimensional Schrodinger equation into three one-dimensional equations. Okay, or the partial differential equation, the three-dimensional Schrodinger equation, which is a partial differential equation, into three ordinary differential equation into three spatial variables. Okay, what do I mean by this? So we want to solve hydrogen atom using Schrodinger equation. We want to calculate the energy levels of hydrogen atom. Remember that we have already done this in the case of using Bohr model. Okay, so let us see what new features emerge by treating hydrogen atom as a quantum system. Okay, a completely quantum system. You can remember that Bohr model was not a completely quantum theory. It involved ideas from classical theory as well as quantum theory. Now, the first complete quantum treatment of hydrogen atom was done by Schrodinger himself in the first four papers. The important four papers that he wrote in 1926. So what we do for solving any system using Schrodinger equation, we should know what is the potential energy. So what is our system is, we imagine that the nucleus is there at the center. We assume that it is stationary, okay, and the electron. Remember the Bohr model. According to the Bohr model, this electron in the hydrogen atom is revolving around the nucleus along a fixed path of radius r. This is Bohr model. Okay, this path can be circular path, and then later the modification by Sommerfeld included elliptical path, etc. But here this picture is not there in quantum model of hydrogen atom. So it is assumed that okay, in the initial treatment we will assume that this nucleus is infinitely heavy compared to the electron, so that it is stationary. Okay, and this electron is just existing around the nucleus. You can think about it something like an electron wave, okay, existing around the nucleus. So there is no such picture here. We can think about an electron cloud if we want, or electron wave around the nucleus. So the average distance of the electron from the nucleus, or the instantaneous distance of the electron from the nucleus, let us treat it as r. Then what is the potential energy when the electron is at a distance r from the nucleus? It is the Coulomb energy, right? So minus E square by 4 pi epsilon 0 into r. The nucleus has plus E charge, electron has minus E charge. So 1 by 4 pi epsilon 0, Q1 Q2 by r, where Q1 is, let us say, plus E, Q2 is minus E. So this is the potential energy. Now you can note that this is a three-dimensional potential energy. Okay, it is spherically symmetric, and it depends only, in the sense that it depends only on the radial distance r from the nucleus to the electron. And if we want to use Cartesian coordinates, you should write this r as square root of x square plus y square plus z square. Suppose we use Cartesian coordinates with the nucleus at the origin, or the origin at the nucleus. Okay, then the position vector, or the radial distance to the nucleus r, can be written as root of x square plus y square plus z square. So potential energy will involve a square root of x square plus y square plus z square. Then if we want to solve Schrodinger equation, it will be very difficult to separate it into an x coordinate, y coordinate and z coordinate, because these three coordinates are combined together inside the square root of x square plus y square plus z square. But if we use spherical polar coordinate system, you can see that this potential energy nicely depends on only one variable, r, radial distance. It is independent of theta and phi. In that sense, we say that it is spherically symmetric. It's independent of theta and phi. So it is possible that if we write Schrodinger equation in terms of spherical polar coordinates, we may be able to separate it into three variables, three spatial variables. Okay. Okay, so let us proceed. Let's write down the three-dimensional Schrodinger equation. Okay. So the three-dimensional Schrodinger equation is okay. Again, you notice that this potential energy is independent of time. So we don't have to solve the time-dependent Schrodinger equation. The wave function is separable, okay, into spatial part and time part, and the time part is e raised to minus I e t by h cross, right? So we need to, just like as we have discussed in the case of the four one-dimensional problems before, here also potential energy is time independent, so we need to solve only the time independent Schrodinger equation to get the spatial part of the wave function. Okay, so I am writing the time independent Schrodinger equation, but the difference is that it's not a one-dimensional equation. Now it's a three-dimensional equation. So we have del square psi plus 2m by h cross square. This m is the mass of the electron. Okay, we assume that mass of the nucleus is infinitely large compared to the mass of the electron, so that it is stationary. Okay, we will come back to this point and we will modify this idea a little later. Okay, so 2m by h cross square E minus V of r psi. So this is the three-dimensional Schrodinger equation, and as we can see, it's a partial differential equation. It involves spatial derivative of psi in terms of x, y, and z. This del square psi is nothing but dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square if we use Cartesian coordinate system, x, y, z coordinate system. But the problem, as I told you before, the problem with using Cartesian coordinate system is that this V of r has this expression, and if we use Cartesian coordinate system, this radial distance r will be root of x square plus y square plus z square. That means they will be combined together inside that square root. So it may be very difficult to separate the variables in Cartesian coordinate system. So since this potential energy depends on only on radial distance r, it's easier to use spherical polar coordinate system. Okay, and it will be easier. It is expected that it's easier to separate the three variables in spherical coordinate system. So we are going to rewrite this Schrodinger equation in spherical coordinate system. This del square psi I am going to write in spherical coordinate system. Okay, so in spherical polar coordinate system, okay, what is the expression for del square psi in spherical polar coordinate system? It's a complicated expression. So let me write it down. 1 by r square dou by dou r square dou psi by dou r, where psi is our wave function, plus 1 by r square sine theta dou by dou theta sine theta dou psi by dou theta plus 1 by r square sine square theta dou square psi by dou phi square. Okay, this is del square psi. Okay, in spherical polar coordinates. Plus, so this is only the first term in this Schrodinger equation, del square psi. There are three long terms here. Then this second term is the 2m by h cross square e minus v psi. Okay, we will write it here. So 2m by h cross square e minus psi equal to 0. Okay, I can substitute for v also. So instead of this v, let me substitute. What is our v? Look at this equation, minus e square by 4 pi epsilon 0 r. So if I substitute this value here in the Schrodinger equation, then that minus in the negative sign in the potential energy and this minus will cancel. So plus e square by 4 pi epsilon 0 r. Let us call it equation 1. This is our Schrodinger equation in spherical polar coordinates. Okay. Okay, now we know r is radial variable, theta is polar angle, and phi is azimuthal angle. Now this is a partial differential equation. There is dou by dou r, differentiation with respect to r, partial differentiation with respect to r, partial differentiation with respect to theta, and partial differentiation with respect to phi. So one way to solve this equation, or the first step in solving partial differential equation, is to try the separation of variables. Okay, so let us try the separation of variables in this case also. Let us try to rewrite this equation into three ordinary differential equations, one in radial variable r, one in the polar angle theta, and one in the azimuthal angle phi. That's our aim. So how do we do this? So we start with this idea, this unknown function psi. Now it's a function of r, theta, and phi when we use spherical polar coordinate system. This we write as a function of radial variable r only, a function of polar angle theta only, and a function of the azimuthal angle phi only. So this capital R represents the radial wave function, okay, and capital theta represents the polar wave function, or the wave function that depends only on the polar angle theta, and this capital phi represents the azimuthal wave function, or the wave function part that depends only on the azimuthal angle phi. Okay, so let us substitute for psi this product psi in terms of this product of three wave functions. Okay, that's the first step that we are going to do. So let us substitute for psi in equation 1. So when we substitute for psi in equation 1, look at the first term. Here the differentiation here is with respect to r only, and here also it is with respect to r only. So when we substitute for psi as capital R into capital theta into capital phi, this capital theta, it depends only on theta, so we can take it outside this differential symbol in first term. Also capital phi also, it depends only on the angle phi, we can take it outside the differential symbol, because the differentiation here is only with respect to small r. Okay, so I will take substitute for psi here, and I will take capital theta and capital phi outside the differentiation. Okay, they can be treated as constant, the theta part and phi part. So the first term will be like this: capital theta, capital phi, they are taken outside. Okay, 1 by r square dou by dou r square dou by dou r of, instead of psi we have substituted capital R into capital theta into capital phi, and this theta and phi we have taken outside, so there is only r here. Okay, plus, now look at the second term. In second term the differentiation is only with respect to theta. So when we substitute for psi in terms of these three wave functions, this capital R can be treated as a constant there because it's independent of theta, and capital phi can be treated as a constant there because it is independent of phi, where in the second term. So that we can take out capital R and capital phi outside this derivative and this derivative also. Okay, so the second term will be like this: capital R wave function and phi wave function divided by this r square sine theta term is there, then dou by dou theta sine theta dou by dou theta of, instead of psi we have substituted, okay, and only theta term will be inside the derivative. What about the third term? Here the differentiation is with respect to phi, and directly there is a second derivative. So we can take a r wave function and theta wave function outside this derivative. Only capital Phi wave function will be differentiated. Okay. So the third term will be, I will write the third term here, plus capital R capital theta divided by r square sine square theta dou square by dou phi square of, instead of psi now we have only capital Phi part inside the derivative. And the last term 2m by h cross square e plus e square by 4 pi epsilon 0 r, instead of psi we have r theta phi, okay, equal to 0. So we have substituted for psi in terms of r theta and phi. Okay. Now the next part is divide throughout with this r theta phi. That means divide throughout with the wave function. Okay, so let us see what we get. Now when we divide throughout with when we divide throughout with r theta phi, what do you get? In the first term, maybe I will use the, okay, in the first term, this theta and phi will cancel with the r theta phi in the denominator, so only the r term will be there. Okay, so this first term will be like 1 by r, it's a function of r, 1 by r square, and now we can drop this partial derivative, right? Because now the differentiation depends, the function depends only on r. Okay, maybe we will retain for the time being now. So dou by dou r square dou by dou r of capital R is the first term, plus in the second term when you divide with r theta phi, this r and phi, capital R and capital Phi in the numerator will cancel with r theta phi in the denominator. So only the theta term will be there in the denominator. So we have 1 by theta, then there is 1 by r square sine theta dou by dou theta sine theta dou by dou theta of capital theta. Okay. Now in the third term, here r and theta will cancel with r and theta in the denominator, so only the phi term will be there in the denominator. So we have 1 by r square sine square theta, then there is a phi, capital Phi in the denominator, dou square by dou phi square of phi. Derivative is acting on phi. And in the last term, fourth term, this r theta phi in the numerator will cancel with r theta phi in the denominator. Okay, so that the wave function is gone there. So we have the last term will be 2m by h cross square e plus equal to 0. Let us call it equation 2. Okay, so we have substituted the wave function r theta phi, and then we have divided throughout with r theta phi. Now we have this equation 2. Now let us try to separate out the variables. Okay, first of all, I noticed that let's notice that in the third term here, this denominator depends on capital Phi depends on phi, and this second derivative also depends on phi. There is this additional term 1 by r square sine square theta. Okay, And in no other term, in the first term or the second term, okay, in no or the third fourth term, you cannot see phi here. So first thing what we want to do is separate out the phi part. So in order to separate out the phi part, okay, only these two terms, in the denominator you have a capital Phi wave function, and here you have a second derivative on in phi. So if we are able to remove this 1 by r square sine square theta from this third term, that third term will be exclusively depending on the azimuthal angle phi. So what is the obvious thing to do? Multiply throughout with r square sine square theta. So I am going to multiply equation 2 throughout with r square sine square theta. The aim is to make this third term completely depending only on the azimuthal angle phi. Okay, so when you multiply throughout with r square sine square theta, the first term becomes 1 by r. Then an r square is there in the denominator for the first term here. There is an r square in the denominator. When you multiply throughout with r square sine square theta, this r square will go. So we have only a sine square theta here. Then dou by dou r square dou r by dou r plus you are multiplying with r square sine square theta. So there is an r square sine theta in the denominator in the second term. So this will cancel and you have a sine theta in the numerator. Okay. So this is 1 by theta sine theta dou by dou theta sine theta dou theta by dou theta plus, what about the third term? R square sine square theta is completely gone. So we have 1 by phi dou square phi capital Phi by dou phi square plus, and okay, now we have an r square sine square theta extra term here. So let's put an r square sine square theta in the fourth term, 2m by h cross square equal to 0. Okay, now our aim is achieved. In the third term there is phi, only phi, and in no other term you can see the phi part. So I am going to take this phi term to the right side of this equation. Okay, the third term to the right side of this equation. Let us see how it goes. So so we have to be careful while dealing here. Let's don't leave out any term. So sine square theta dou by dou r square dou r by dou r plus second term 1 by theta sine theta okay. Now I am writing the fourth term, r square sine square theta 2m by h cross square equals, I am taking this phi term to the right. So we have minus 1 by phi dou square by dou small phi square into capital Phi. Okay, let us look at this equation now. In this equation there are three terms on the left side. Okay, there are three terms here and there is one term on the right side. The terms on the left side depends on the variables r and theta. The term on the right side depends only on the azimuthal angle phi. Okay. Now when you write such an equation, on one side you have two variables and the right side you have one variable, a different variable. Then suppose you will consider this possibility. Suppose phi remains constant and only r and theta changes. Okay, when r and theta changes, let us assume that the left part of this equation increases. Okay, that is, this capital R function and capital theta function will change. Let us assume that will change in such a way that the left part of the equation increases. Then what happens? The left side of the equation will increase, but see, the right side is independent of r and theta, so it will remain the same. Then this equation will be violated. Okay, and this equation will not be valid. And in the same way, let us assume that this r and theta, small r and small theta, radial variable and polar angle, they remain constant, and azimuthal angle phi changes. And suppose the right side of the equation, this capital phi wave function, is in such a way that as azimuthal angle phi increases, suppose the right side of the equation increases, then also left hand side is independent of azimuthal angle phi, so left hand side will remain the same but the right side increase, then also the equation is not valid. Okay, so this equation to be valid for all values of r, theta and phi, then the only possibility is that left hand side of the equation as well as right hand side of the equation should be equal to the same constant. Okay, left hand side depends on two variables, right hand side depends on a third variable, and still it's an equation. The equation should be valid. Left hand side should be balanced by right hand side. This is possible only if left hand side and right hand side equal to the same constant. So let us introduce a constant here. So I will let us put this, what was our equation number before? Equation 2. So let us consider, give an equation number 3 for this equation. Equation 3. And in equation 3, I will first equate right hand side with some constant, and the left hand side should be equal to that same constant. So let us look at the right hand side now. So let minus 1 by phi, okay, dou square phi by dou phi square, there should be capital phi in the numerator, okay, equal to, we are introducing a constant. Let me use this symbol ml square. Why do we use this particular symbol? This is in anticipation of some results that we will be able to write down later. Okay, so we can use any symbol equal to some k square, c square, a square, any symbol we can use. I am using this symbol, and this is a constant. When we introduce such constants during the separation of variables of a partial differential equation, we call them separation constant. So this is one separation constant. Okay, before going back to equation 3 and equating, so the left hand side of equation 3 also should be equal to the same constant ml square. But before that, let us spend some time here. Let us rewrite this equation. Now this is we can call it a phi equation. Okay, phi in the sense that it's an equation that depends exclusively on the azimuthal angle phi. Let me rewrite this equation. First of all, I noticed that since this capital phi, okay, this capital phi, it depends only on the azimuthal angle phi. We don't have to use partial differentiation symbol here. It's a full derivative we can use. Okay, so and also I can take this capital phi to the right side. Okay, and I can combine write all the terms to one side. So this will be like d square by d phi square. So instead of partial differentiation, I am using full differentiation of capital phi, because capital phi depends only on one variable, plus ml square phi equal to 0. Right? This equation can be rewritten like that. They take this capital phi in the denominator to the right side, so it is ml square phi, and take this second derivative also to the right side. So all the terms are positive now. Okay, let us call it equation 4, and this equation we may call the phi equation. Okay, we have separated out, okay, let me mark it. We have separated out one ordinary equation from the partial differential equation, and this ordinary differential equation depends only on the azimuthal angle phi. So let us call it simply Phi equation. Okay, and we will come back to this equation later and see how we can write down the solutions. Let us, for the time being, let's go back to equation 3. So far we have written the right hand side, we have equated as ml square. So left hand side should be equal to the same constant ml square. So let us look at equation 3 and let us write down left hand side equal to the same constant, right? Okay, so I will write here what is that 1 by r sine square theta. Maybe here also let me use full derivative, okay, because the functions inside these derivatives now depends only on one variable, r square dr by dr plus 1 by theta sine theta. Full derivative I am using here also, because capital theta depends only on small theta, plus r square sine square theta okay, equal to, this is the left hand side of this equation, equation 3, right? 1 by r sine square theta. Yeah, only change is that instead of partial derivative I have used full derivative also. Yeah, 2m by h cross square. Yeah, okay. Now the right side I will be equal to this constant ml square, right? Okay, so this is equal to ml square. Now we want to you look at the left hand side, it depends on the radial variable r as well as the polar angle theta. We want to separate it. So what is the way to do it? Yeah, so one way is look at the first term. It depends on the radial variable r, right? But there is a sine square theta here. And look at the third term. It also depends on the radial variable r. Okay, there is a constant here. It's a total energy. Okay, we will deal with this total energy a little later. So for the time being, apart from this, we don't this total energy may contain different energy values. Okay, okay, we will consider that a little later. Apart from this expression, complete expression for total energy, we can see that this potential energy term depends only on r. There is an r square here. So if we can remove this sine square theta, this term, third term, also looks like it depends only on the radial variable r. So the first term also only a sine square theta is there. The other terms are also depending on radial variable r. So we can remove this theta dependence from the first term and the third term if we divide throughout with sine square theta. So let us do this. We are going to divide throughout this equation with sine square theta. Then what happens? The first term will be 1 by r, sine square theta is gone now, so d by dr, r square dr by dr. In the second term, if we divide with sine square theta, there is a sine theta in the numerator here. Okay, it will cancel with the sine square theta in the denominator, so there is only a one sine theta in the denominator now. Okay, so we have 1 by theta and 1 by sine theta, d by d theta. In the third term, this sine square theta is gone, so we have 2m r square by h cross square. Right side you have a sine square theta because you are dividing throughout with sine square theta. Okay. This is the next, let us call it equation, or we will, in the next term we will write that. Now if you look at this equation, um, our aim is actually the first term depends only on radial variable, and the third term looks like apart from this constant E, the total energy, which may involve radial and angular terms. The third term also looks like it's depending only on radial variable r. So the second term depends only on the theta variable. Now there is no radial variable. So I will take and look at the term on the right side. It depends on theta variable. So I will take this second term to the right side, so that on the right side we will have only theta variables, and the left side we will have only r variables. Okay, that's our next step. So we have 1 by r d by dr, r square dr by dr, plus, now let me write the third term now, 2mr square by h cross square e plus. Okay, this is the left hand side, and on the right hand side already we have ml square by sine square theta, and I will take the second term from here, the above equation. This term I will take to the right side. Okay, so there is a minus sign, minus okay. Let us call this equation 5. That's the next number, right? Yeah, equation 5. Look at equation 5. Now right hand side depends only on theta, left hand side depends only on r. By going back to our previous argument, this is possible, and still the equation is valid only when right hand side and left hand side are equal to the same constant. So let us introduce another separation constant here. Let me first write down right hand side equal to some constant. Okay, so I will equate the right hand side equal to some constant. So let us say this ml square, let ml square by sine square theta minus, okay, this is equal to, I have to introduce some constant, and I am introducing this constant L into L plus 1. And let's again, don't worry about this peculiar form of the constant. Instead of writing simply some C1 or C2, I have introduced a constant in this form. This is to facilitate some solutions a little later. Okay. Okay. So this is in anticipation of some results that we are going to obtain later. That's it. Okay. So let me simply try to rewrite this equation in a neat form. So what I am going to do is, I will take all the terms to the right side, so that this first term will become negative and the second term will become positive, and I will multiply throughout with capital theta. Okay, so that capital theta will go from the denominator, so that we have 1 by sine theta d by d theta okay. This term has gone to the right side. Okay, so it's positive. Now we have L into L plus 1, and then this first term ml square by sine square theta, when it comes to the right side it becomes negative, so minus ml square by sine square theta, and the whole thing is multiplied with capital theta. This is equal to 0. Let's call it equation 6. Okay, let's call it equation 6, and look at this equation. It depends only on theta, and this equation let me call theta equation. This is our theta equation. So we have done again the separation of variables into the second ordinary differential equation, which we call theta equation. Okay. Again, let's go back to equation 5. In equation 5, the right hand side we have equated to the constant L into L plus 1. So the left hand side should also be equal to the same constant. Okay. So let me equate the left hand side equal to the same constant now from equation 5. So equation 5 becomes 1 by r d by dr r square dr by dr plus 2mr square by h cross square e plus e square by 4 pi epsilon 0 r is equal to L into L plus 1. Okay, so let me combine these terms. So what I am going to do now is I am going to write down this in a standard form. So I will first divide throughout with this r square, so that in the first term you will have an r square in the denominator, and in this second term r square will go. Okay, and then I will bring this L into L plus 1 from the right side to the left side, so it becomes minus, and r square will come in the denominator of this equation, this term also. Then I will multiply throughout with its capital R, so that capital R will go from the denominator. Okay, so it's just a rearrangement. So what I am doing, I am dividing throughout with small r square and then multiplying with capital R. So this equation becomes 1 by r square d by dr r square dr by dr plus in this term small r square will go because I have divided throughout with. Okay, so 2m by h cross square e plus e square by 4 pi epsilon 0 r. This L into L plus 1 is on the right side you have L into L plus 1 by small r square. If we take it to the left side, we have L into L plus 1 by small r square, and this whole term will be multiplied with capital R. Okay, it's a function of r. This is equal to 0. This is our next equation. What is equation number 7? This is equation 7, and this equation we can call r equation because it depends only on the radial variable r. So this is the third ordinary differential equation we have separated from the three-dimensional partial differential equation. Okay, so now we have got a an r equation, a theta equation, and a phi equation. The three-dimensional partial differential equation, Schrodinger equation, has been separated into r equation, theta equation, and phi equation. R equation is there, equation 7, theta equation is there, equation 6, and phi equation is there, equation 4. So this is the first step in trying to solve the Schrodinger equation. Now in the next class we will consider each equation separately and we will look at the solutions. Okay, thank you.